So we're going to start talking about probability distributions of discrete random variables. And then when we get to the next chapter, we're going to start talking about probability distributions of continuous random variables. So we're actually going to be focusing on these probability distributions for quite a while, actually. So let's get started then. So let's talk about what we mean by a discrete distribution for a random variable. So let's suppose we flip a coin. Well, then the sample space is either you get heads or you get tails. So notice that this is what we mean by discrete, right? There's nothing in between heads and tails that you can get. You either get heads or you get tails. That's an example of a discrete type of distribution. So, of course, we're going to try to start analyzing these things mathematically. To do it mathematically, it's probably better to try to assign a number to each of these outcomes. So we're going to define a function. We're going to call that function x, and it's going to take an input as an input for something from the sample space, and then we're going to assign to that input a real number. So again, we're changing these possible outcomes to real numbers, essentially. So in this case, let's say that when we assign to the heads flip 0, and we assign to the tails flip 1. We're flipping a coin here, so certainly it takes on these values 0 and 1 randomly. It depends on when you flip it, whether or not you get a 0 or a 1. And again, like I mentioned with the HT idea, the set 0, 1 is a discrete set, right? There's nothing in between 0 and 1 here that you can possibly get as an outcome for the x. So therefore, in this case, we refer to the function x as a discrete random variable. All right, so just to define this more generally, let's say S is the sample space of a random experiment, and X is a function that again assigns to elements of the sample space a real number. Then we refer to X as a random variable because again it's a function that's coming from a random experiment, and since it's taking on values rather than just outcomes that are in a sample space, since it's taking on values, we can think of X as a variable. And then we notice over here in our function notation, remember we have domain and codomain. S is the domain here, and we use a fancy word when we're talking about domains for random variables. We refer to S as the support of X. Basically what the support means, it's going to be the places where the X has, well, it's places where X is actually defined. All right, so what we're interested in, of course, is the probability that the values that X can take on. So what we mean instead here is the probability that capital X equals some little x. Remember, X is referred to the variable. The little x here is going to be some specific value of the random variable. So we're interested in the probabilities that our random variable takes on a specific value for various values of x. So typically, we denote this by a function. Usually, we use an f. The letter doesn't matter. It's just f is usually the first one we get to. So we call f of x here the probability mass function, or PMF of x. So I use PMF just as for short, because saying probability mass function over and over again gets a little bit tiresome. All right, so we already know the properties of probabilities, right? If we have a probability function, we know what those have to satisfy. So that tells us what the properties that PMFs have to satisfy, but let's just run through them. Certainly, if we're going to do the values of x that are actually in the sample space, so those values that can actually happen, then those probabilities all need to be positive. We certainly can't have negative probabilities, and we're assuming it's in the sample space, so it actually can be an outcome, so it has to have some non-zero probability. That's what this statement's saying. Certainly, if we add up all of the values of the PMF over the entire sample space, we have to get 1. Because again, this is just saying that we're adding up all the probabilities, all the possibilities for the probabilities, and we know we have to get that 1. We have to be 1 for that case. If we want to figure out the probability of an event, remember a subset of the sample space is an event, then the way we can compute that with the probability mass function is to take all the x's, take all the values that are in the event, and then plug those into the probability mass function and add them up, that basically is the probability of the disjoint sets idea. We've got very different values that since we have a function, since we have a random variable here, that random variable can't take on two different values at the same time. So the probability that capital X would be a little x1 and the probability that capital X would be a little x2, those are mutually exclusive. So if you did the probabilities, you would add them together. That's all this statement is saying. So this is following the OR statement for probability, as long as they're disjoint sets, right? Disjoint events, mutually exclusive events, I should say. This is just that the probability of the sample space is 1. That's all that's saying. All right, so let's do an example here. Let's say we have a random variable that has support 1, 2, 3, 4, and then we have the PMF, f of x is x over c, whatever that c happens to be. So in this problem, it asks you to find the value of c and then find the probability that x is 2 or x is 3. Now let's figure out what the c is first. From that second property that we talked about on the previous slide, we know that if I add up the PMF over all the possible things in the support, I have to get 1. So this gives me an equation to solve. I know that the sum from x equals 1 to 4, because those are my possibilities in my support here, of x over c has to be 1. Now, just plugging in the various values of x, in simplify we get 10 over c has to be 1. So that tells us that c has to be 10. For the second part now, we want the probability that x is 2 or x is 3. Well, the probability that x is 2 is given to us by f of 2. Probability that x is 3 is given to us by f of 3. And since they are mutually exclusive, I just need to add the probabilities together. There's nothing to subtract. So in this case, when we add those two probabilities together, again, we figured out the value of c. X is 2 here, so I get 2/10. X is 3 here, I get 3/10, so we get 1/2 for our probability. All right, so later on in the semester, we're going to be more interested in shapes of distributions, especially when we get to continuous random variables. To help us for that with discrete, they take on the form of what we refer to as probability histograms. So let's see what we mean by that. So to create a probability histogram for that previous example, the first thing we're going to do is we're going to compute all of our probabilities. Our support was 1, 2, 3, 4. So we calculate those probabilities by plugging into the x over 10 function again. And then if you're familiar with histograms, you know basically it's like a bar chart. The probabilities are going to be the heights of our bar chart. And then we're going to center the bars at each of our values in the support. So we get something that looks like this. So this would be our probability histogram. Again, not exceptionally interesting in this particular case, but it is something that we're going to be interested in later on the semester as we shift over to continuous distributions. We'll do more examples of these in class, as well as more examples that look like what's on the next video, which you should go watch now.